to our client-server communication protocol workshop. First of all, I hope you're all doing well. So a few words of introduction. This session will be the first of 3. And those of you who complete all will be rewarded certificates to indicate your successful completion. We'd like to give a huge thank you to the Syrian Society of EMU for collaborating with us. As Aquabotics, we're a team of engineering students that design and develop autonomous underwater vehicles. At the same time, our members are also trying to provide online learning resources during these times. And in today's course, we're also joined by Professor Dr. Erhan Ince. For those of you who don't know, Dr. Ince is currently a professor in the Department of Electrical and Electronics Engineering. His research interests boast an impressive scope, including channel coding, multi-carrier techniques, performance bounds, and statistical signal processing. So a really big thank you, Dr. Ince. We're grateful for your joint efforts. Dr. Ince will be speaking about wireless communication in the first part of this course and its importance, followed by graduate member of Aquabotics, Rahman Bekawi, who will be focusing on implementation of MCUs. So for today's course, what you will need is the Arduino IDE installed and 2 NodeMCUs. We encourage you to use the chat option if you have any questions, but preferably keep any questions until the end of the session, as we will be holding a Q&A session. Today's course is going to mark the beginning part of our Guide to Industrial IoT series. And like I mentioned, there will be 2 more after this. So without further ado, I'd like to invite Professor Dr. Ince to begin. Thank you all. Sir Kiras?
Thank you, Anna, for the nice action, and also Aquabotics and the Syrian Society for organizing such a nice seminar. I hope the students will enjoy it and benefit from it. I'm going to talk about wireless communications at the beginning, and then I will hand over to Mr. Erhan Bekawi, and he is going to tell you about some hardware. Okay. As you all know, which is why is not using an electrical conductor actually. For example, the most common technology that is like this is using the radio spectrum. For example, when you pick up your mobile phone and you want to talk to your friend, between your mobile and the base station antennas, there will be radio signals transmitted and received, depending on if you're initiating the call or you're receiving the call. Okay. With radio waves, we can have short distances. For example, you can pick up your TV remote and change the channel on your TV. Here we're talking about short distances, few meters. Or we can talk about thousands or even millions of kilometers. For example, you can talk about deep space communication. This means a long distance, the satellites from us. So we can talk about thousands of kilometers of distance. Well, first of all, we want to differentiate between the different types of spectrum. If we want to talk about the entire range of electromagnetic radiation frequencies, we call it the electromagnetic spectrum. So what is the radio spectrum? Radio spectrum is actually from 10 kilohertz to 300,000 megahertz. And it is divided into a number of bands, this radio spectrum. We can have very low frequency, all the way up to extremely high frequency bands, okay? And as you may already know from some of your classes, there's a link between speed of light, the wavelength of the signal, and the frequency of the signal. If the frequency goes up to have the speed of light be constant, the wavelength has to go down, okay? This is important because sometimes we need to choose a high frequency for our applications so that our signal can be transmitted to a longer distance without losing most of its energy or power. Okay. For example, in this slide, you can see your mobile communicating with the router through Wi-Fi, some sensors communicating with the router through Bluetooth, and other sensors using Wi-Fi radio. So in our daily life, as you can understand, we use a lot of wireless technologies. So do we have some advantages and disadvantages? Yes, as always we do. For example, if you are a working professional and you need to have access to the internet in order to do your job, and do your job anywhere you are. I mean, not only at the workplace, maybe on the road, maybe at home, okay? Then wireless internet is very good for you. Since you can do your job, you can actually improve productivity, okay? Also, wireless communication can be a very good option in, for example, hazardous areas where you cannot lay cables or it's difficult to lay cables. And it's also useful, for example, when you have no cables, you have tidier environments, okay? What about some disadvantages? Some disadvantages may include the following, for example, because information is transmitted in packets, wireless-wise, sometimes there may be security vulnerabilities. You know, you need to have good encryption. High costs for infrastructure at the beginning, of course, because you have to have base stations to cover the entire geographic area. And influenced by physical obstructions. What are these? For example, climatic conditions, interference from other wireless devices. So, you know, wireless communications has some difficulties in that sense. And any sort of noise or inter-symbol interference that is encountered must be dealt with by using, for example, equalizers and so on. There are actually a wide range of wireless devices. Some of them are mobile devices, some of them are fixed devices, short-range devices, devices for broadcasting, etc. For example, you know about the cellular technologies, which mobile phones use. Second generation, third generation, WiMAX, 4G, the technology that we are using, some mobile meshes, and maybe emerging technologies like cognitive radio and software-defined radio, okay? Well, fixed devices, they are mostly point-to-point or point-to-multipoint communications. Short-range devices, wireless LANs may be under this. For example, 802.11 family, most of the Wi-Fi technologies, or Zigbee. Zigbee is like based on the IEEE's 802.15.4 personal area network standard. Actually, it's an alternative to the Wi-Fi or Bluetooth, and you need to buy the firmware in order to use it. wireless PANs, wireless personal area networks, basically, Bluetooth high-speed variants of the Y media and UWB RFIDs, okay? Or for broadcasting, analog and digital broadcasting or mobile broadcasting. Well, most of the cellular works have been carried out in Europe and in America by IEEE. In Europe, there were two groups that were formed. The first one, FreeGPP, and then the second one, FreeGPP2. And in States, IEEE, okay? So the work started with GSM, then went on to GPRS. GSM, as you can see down here, is the Global System for Mobile Communications. Then General Packet Radio Services was developed. Enhanced Data GSM was later on developed. Universal Mobile Telecommunication System, UMTS, was developed. High-speed download packet access, upload packet access, and so on. Then LTE came, then LTE Advanced, and maybe LTE Pro. Advanced was followed by LTE Pro. When you compare, for example, some of the technologies that was developed by FreeGPP to FreeGPP2, you see, for example, in FreeGPP2, CDMA and CDMA FDO, okay? Basically, these are alternatives to the GSM, the CDMA, and initially CDMA was used by the military, okay? On the other side, IEEE worked on a standard called WiMAX. First, they worked on the fixed WiMAX, which was 802.16. This was then followed by the mobile WiMAX, 802.16e. More specifically, the E is missing here, 802.16m later. But in the long run, FreeGPP's LTE and LTE advanced technologies sort of won the fight between WiMAX and LTE, because LTE and LTE Advanced was using technologies which would use the infrastructure that was there, whereas WiMAX would need to replace most of the infrastructures, and as you know, companies would not prefer this. And here you can see the evolution. The 1G, initially it was just voice. The 2G, the GSM in the 1990s, some mobility, roaming, a speed of 9.6 kilobits per second. Then we moved to 3G that was using UMTS. This is around 2003, speeds of around 2 megabits per second. You notice that this is about 200 times faster than the initial 2Gs. 4G, the architecture was changed a bit. Efficiency was important, and the speed became 300 megabits per second. And then LTE Advanced came. In this LTE Advanced, you can have very fast speeds. And 5G is pending, actually. There's no real standard for 5G. But people are working on it. And as you know, some countries like China and Korea, they are both producing and employing, okay? Do we have any limitations? Yes, due to the competition between countries and companies, lack of industry-wide standards is a limitation, if you ask me. Because if you had industry-wide standards, everybody would put their minds on the job and do a lot more, and maybe we'll come up with something much faster. And there are some device limitations. Not always all devices use hypertext transfer protocol. So this is an issue. What about challenges? We have some challenges on the network and the device. As far as the device goes, the size and how much power it uses and how much it will cost, these are some of the challenges. And you also, nowadays, most technologies in LTE use multiple input, multiple output, so MIMO technologies. So you have to put MIMO in silicon. This is also a challenge as far as the device goes. Network-wise, most applications nowadays are demanding, and reliability is important. When people want to use something, they want to make sure that something wrong will not take and the data will not be stolen or someone will not tap into it. And ubiquitous coverage, what that means is that you're going to have the same service everywhere at the same time. This is also a challenge because same quality service to everyone everywhere at the same time is difficult to handle. Okay. Okay, so what applications of wireless technology are there? We have mobile telephones, wireless data communications, Wi-Fi, cellular data services, mobile satellite communications, wireless sensor networks, wireless energy transfer, wireless medical technologies, and computer interface devices. So as you can see, a big long list of things to do, and wireless is used almost everywhere in our daily lives. Okay. What sort of services they provide? They provide broadcasting, paging, cellular phones, trunking, radio, wireless local area networks, personal area networks, satellite cellular communications. Okay. Well, wireless communications has evolved significantly over the past several decades. And this has to be done in order to meet the demands of high data rates and reliability. Okay. And system had to be designed for indoor and outdoor applications. And specifically, they had to come up with designs that will answer the mobility problem. So mobility is a very important aspect of the system specifications, actually. And one of the key elements in the design of such systems is understanding of the wireless channel. The information, actually, when you transmit it as an electromagnetic wave, is going to be transmitted in the communication channel, or the transmission medium, as we call it. And in order to do a good design, you need to understand the channel itself. Okay. Uh, the wireless signal actually propagates in space based on laws of physics. And electromagnetic radio frequency, which we call RF, uh, travels in a medium and suffers some attenuation, which we call the path loss, okay, based on the nature of the medium. For example, the medium can be under the ocean, seawater. It could be vacuum. It could be over a marsh area or mountainous area. So medium can be anything, actually. In addition, okay, other than just facing some attenuation and losing some of its energy, in addition, the signal encounters some other phenomena like reflections, refractions, diffractions, scattering, etc. The cumulative effect results in the signal getting absorbed or signal traversing multiple paths. You see, when the signal traverses multiple paths, we talk about multipath channels. And at those times when there is no direct path, we talk about non-line of sight communication. And signals frequency being shifted. This is another effect, cumulative effect, due to the relative motion between source and object, and we refer to this as Doppler effect. Okay. So this slide actually shows you a reflection, a refraction. Refraction is how the electromagnetic wave bends when it goes from one medium to a second medium, which have different densities. Diffraction is shown here. Absorption, that the signal is completely absorbed, there's nothing that continues. Or scattering, if you have a multi-surface in front of the electromagnetic wave, for example, leaves for a tree, foliage, there are many reflections which we call scattering. For example, this diagram here shows a transmitter, a UAV with a transmitter receiver, and a transmitter receiver here. You can have a reflected path from the building that goes to the UAV, you can have a direct path. Sometimes there is always the direct path, which is very good because when there is no obstruction, you receive the signal clean, just with a little bit of attenuation, but no intersymbol interference. So line of sight communication, we call this. In Rayleigh channels, we don't have a direct path. In Ricean channels, we do. You may diffract around the buildings, or you may scatter from the trees, as I have said before. Okay, so these phenomena are the phenomena that affect how the receiver is going to receive the signal. Because if you receive one path directly, one which is reflected, one which is scattered, and so on, these, as you will understand, will arrive at the receiver antenna at different times, and they will also, due to the reflections or refractions or scattering, lose some energy. So the components that you receive arrive with different powers, and they arrive at delays, different delays. That is the difficulty of the multipath channels. Let's speed up a little bit. Let's talk about absorption a bit. Absorption, for example, occurs, it says, when the propagation, when the signal propagates through solids. For example, Wi-Fi and buildings with some metal structures will attenuate your signal around 10 to 25 dB. Those of you who took communication 1 with me this semester, you know that 30 dB is a very good ratio. Signal to noise power ratio is around 1 to 1000. So if you're losing anywhere from 10 to 25 dB, you're losing a lot of power, and your signal starts to look like noise. Okay. The trees also attenuate due to the scattering. This attenuation is around 10 to 12 dB. Of course, metals, in fact, attenuate the most. Okay, so do not build a metal infrastructure if you can. Okay, these are some explanations about diffraction and scattering. I will pass these. I'll show you here a Rayleigh channel and its frequency response. The amplitude of a channel, which is modeled as a zero mean complex Gaussian random process, has a Rayleigh distribution. Okay, because of that, because of the name of the distribution, we also call it a Rayleigh channel. Such channels are called Rayleigh channels and occur when there is a non-line of sight communication, which means this. We do not have this direct path. Non-line of sight means no line of sight path. Okay. What that means is there will be lots of reflections, many components arriving at different times and with different powers. So when you look at the frequency response characteristic and you plot the instantaneous power versus the time, you have the Rayleigh fading frequency characteristic, as you can see here, and these are called nulls, deep nulls. These deep nulls are not very good. If you have deep nulls, you can actually encounter some problems in your communication. So when we want to look at this frequency response characteristic, the reason is we want to see if there is deep nulls or not, because if there is, we need to do something about it. Okay. And most of the time, this sort of thing occurs when there is a lot of intersymbol interference, which means the symbols overlap when they are when they are expanded in time. Okay. This is a slide about the transmission scheme. You have some pulses with some amplitudes. The linear combination is your signal. You have your transmission channel with an impulse response h of t. And AK is like polar line code, +1, -1, as you may have remembered from class. So in the channel, you go through like a filter almost. You can think of the transmission channel like a filter. And there is also, in addition to that, white Gaussian noise added. So you have intersymbol interference plus noise, and then you receive the signal, which is a noisy and changed version of your signal actually at the receiver. There is a filter at the receiver also, and you have a sampler. So this is more like a match filter. And then you make some decisions using some threshold. And this is the process that takes at the transmission. Okay. After the reception, you're filtering it. So you see here, there is a filter. So from the emitted signal to the receiver and filter one, when you think about in frequency domain, we'll have an equation like this. And this mu is known as the normalization factor. So after sampling, after the sampler here, we'll have three components that come out. One is the contribution of the ith bit. AI is the, as you know, the bit that is here. Mu is that normalization factor that multiplies it. So this is the contribution of the ith bit. This is the intersymbol interference. Okay. So these are shifted pulses. The channel actually spreads the pulses, so it also shifts them. And these are the amplitudes. So this is the intersymbol interference, and this is the filtered and sampled noise. So mathematically, if you want to think about it, this is the math of the communication channel and the signal being transmitted through it. And these are the three components at the receiver side. As you have seen in this one, transmission channel has an impulse response, and this impulse response sorry. What happened? This impulse response actually can be modeled like a tap delay line FIR filter. We can say the alpha L's are the random coefficients with certain probability density, and the tau L's are actually the delay of the Lth multipath. So we can model the impulse response of the channel by a tap delay line FIR filter. If you do a little bit of reading on communications, you would see that there are tables for specific channels, for example, channel A or channel B types. The difference here are the maximum delays. Here we have 310 nanoseconds. Here we have 700 nanoseconds. The more the Doppler, the channel may change. Of course, the more adverse the channel becomes. Okay, so here you see the number of taps, and you see the relative delays of tap, and you see the relative average power of each tap. Okay, so when you get a table like this, you're actually getting the power of the components that you receive and the delay that you had when you received them. Okay, so from these two pieces of information and the number of taps, one can model a channel on the computer environment. Okay. Actually, if your channel is going to be a flat fading channel, as it says here, it's going to have a single tap FIR filter. So we do not need all these taps. One would be enough. And the attenuation would be constant, flat fading, as it says. All right, so what's the future 5G new radio is the future. Why NR? It's going to provide higher data rates and much less latency than what we have nowadays. I mean, from about 30 to 1 millisecond they want to go. Evolution of LTE is constrained by backward compatibility. For example, when you build something, it doesn't handshake with the old technologies in LTE. So 5G new radio wants to solve this issue. Legacy devices should be able to access um, an evolved carrier must come out. Okay. So under 5G, we have some use cases. What are they? Enhanced mobile broadband. We are desiring peak speeds of around 20 gigabits per second. And in the edge area, when we talk about edge, I mean the edge of the geographic region or the cell you are in, around 100 megabits per second. As you know, when you are far away from the base station and just between the two cells, you are at the edge. This is the more difficult part because your mobile is about to make a handshake with the other base station, and you are further away from two of the base stations. That is where most of the time you may encounter problems if your phone call is broken, okay, because you cannot do a correct handover, okay. On the other side, the other two use cases are ultra reliable and low latency applications as low as 1 milliseconds and very, very low error. I mean, this is 10 to the minus 9. In the past, we were talking about 10 to the minus 6 and so on. So they will be ultra reliable. The bit error rates will be very, very small. Okay. And the third one is massive machine type communications. Millions of devices will connect in 1 kilometer square, and there will be high energy efficiency. Okay. Of course, this also brings with it some question marks as far as the antennas, because we will have in the millimeter wave technology, we'll have many antennas. So having many antennas, is it going to create any problems for the health issues? This is being discussed. Of course, there is no research out there that showed so far that it is going to be harmful. So till so, I think 5G is going to continue. 5G new radio is going to use both LTE and the new radio. So it's not dropping the LTE and LTE at once. It's going to make use of them. So it's going to be a heterogeneous development. In macro cells, LTE will be deployed at lower frequencies. And in smaller cells, which we may call picocells or femtocells, we will use the new radio, and this will be at higher frequencies. Okay. So this dual connectivity will provide higher network robustness. I mean, also when the macro cell cannot support the because you're the other picocells or femtocells will try to support the users. Okay. All right. So finally, I want to bring our attention back to the third application, the Wi-Fi. As you know, Wi-Fi is the name of the wireless networking technology, and it's under the IEEE 802.11x standard, if you may say. Sometimes there is a misconception that Wi-Fi stands for wireless fidelity. This is not true. This is a misunderstanding. So you must also understand that. The first 802.11 technology came out in 1997, and in 2019, 802.11ax came out. We call this Wi-Fi 6. As they develop the routers, and as they increase the data rates, they develop different standards, and they have different names: BAG and ACAX. etc. Okay. Here in this table, you can see data speeds, maximum data rates for the different standards. As you can see, in 802.11ax, the one in 2019, envisioning 10 to 12 gigabits per second speed, maximum data rate. Whereas in 802.11a, which was in 1999, we were doing around 54 megabits per second. Okay. Why do I say about this Wi-Fi? Because today, right, I'm going to talk about one more slide and hand over to Mr. Bekawi. Mr. Abdel Rahman Bekawi is going to present you NodeMCUs. What are NodeMCU? A NodeMCU is a system on a chip which is designed for open source IoT platform by Expressive Systems. They actually use Wi-Fi, built-in Wi-Fi. They have Wi-Fi capabilities. That's why I mentioned Wi-Fi a little bit. The firmware uses some scripting language. This could be Lua or some other language. And the Wi-Fi communication between the NodeMCU boards is going to be discussed today. For example, you can think about ESP8266 as an access point, which will be set up as a server, and another one set up as a client. So these will be exchanging measurements they read, for example, from sensors, and the server will collect the readings, and clients may be logging into the server and obtaining it. They'll be using HTTP to do requests. So with this, I want to hand over to Mr. Bekawi to continue his talk about client-server computing using NodeMCUs.
All right. Can you hear me?
Yes, we can hear you fine.
Okay. Thank you so much, sir, for your great presentation. I would like to thank as well our software lead, Amina, for her introduction, and big thanks goes to the Syrian Society President, Abdel for making this happen. A big thank you for you all to be part of this. I hope you will enjoy it and see it useful. Let me share my screen first. All right. So let's now jump into the motivation of why you should start using the NodeMCUs. Actually, the NodeMCUs, as Professor Erhan Ince said, it uses the scripting language, Lua, but we are going to use the Arduino IDE for that instead. So because it is much easier for us to use and it is an open source. What is the importance of NodeMCU? Actually, it is about the wireless communication property will give you the ability to build any IoT application. But the good thing about it, if you think of an Arduino development board, you will see how useful it is and how easy to use, how powerful, how many, like by connecting the peripherals, the GPIOs, general purpose inputs and outputs, and so on. So combining both wireless communication and the ability of any Android Arduino development board will open up many fields for us. For instance, we will be talking about the IoT, Internet of Things. The IoT use cases nowadays could be for the e-health, the smart home and city, mobile and transportation, the Industry 4.0 combined with the AIs, and the everyday things. An example of an everyday things, if you think in winter, like when you wake up, it is a bit hard to wake up, but you can build an application to switch on the heater before you go to the bathroom, or maybe just to set a timer for the heater to switch on, and then you wake up, you will find the hot water waiting for you. This could be done using the NodeMCUs, and after the end of this session, hopefully you will find you'll be able to do this if you wanted. But if you are not familiar with electricity, it's not preferred to deal with mains power supplies. All right. Before we go into the hardware, we will be talking about the model used in this session. We have a single server serving different clients. One of the clients is going to be sending a button state to the server, and then the server will update this button state information to a third client, a second client, and that client is going to be a web page. So we'll take the information from the first client and then send it back and update the value in the web page, which is the second client. A third client will be also sending an analog value by the use of the analog to digital converter. And also this information will be passed to the web page client and to be displayed on the website. So by this, whenever you want to go to that website, then you will be able to refresh the page to see the new and modified values. Okay. So let's go into the hardware. The hardware is pretty simple. I'm using 2 NodeMCUs and 1 WeMOS D1 Mini. The WeMOS D1 Mini is basically, again, an ESP8266 enabled microcontroller, but it is much smaller and much less in cost. Unfortunately, I couldn't find the NodeMCU model and the fritzing when I was drawing the circuitry, but it is going to be the same. So to start off, the server circuitry, I will be connecting an LED through a resistor back to ground through one of the digital pins to use this later in the code. The first client will be connected to a button state, and this button state will be connected to the input pull-up resistor of the built-in the ESP8266. I'll talk about this more later. And then back to ground. The second client will be connected to the potentiometer in order to give me an analog value from 0 to 5 volts, but this value will be converted to 0 to 1024 bits. So enough about the hardware. Let's go and let's have some fun. Let me open up Arduino and share the screen. All right. Right now, I'll start from the very beginning. I'll start from scratch, coding the server side. Don't worry if you are not familiar with Arduino or you have no idea how to program Arduino. I'll explain each line of code. And if you have any questions, please write them down in the chat session. First of all, let me save this into the desktop and call it a server. Okay. To start off, we need to include 2 libraries for the server. One of them is going to enable us to connect to Wi-Fi, and one of them is to declare the web server. And for this, we'll be using the ESP8266 Wi-Fi.h. And the second one, the first one actually will be enabling the Wi-Fi connectivity. The second one is going to be ESP8266 web server.h. Okay. So there are some variables need to be considered before we move on, and they are actually a constant values. So these are actually the Wi-Fi credentials or the Wi-Fi access point you have or the router. And for this, we need the SSID and the password, the Wi-Fi ID or the name. And for that, I'm going to use a character array and call it an SSID. And this is going to be my Wi-Fi network name. And the second one, I'll be using the password. You can use any of these, the SSID in this way and the password in this way. They both have a character array. They both have the same type. Okay. Note that these has to match your Wi-Fi credentials, your Wi-Fi access point. Okay. So now we have the ID of the Wi-Fi and its password. Then we can go and just connect to Wi-Fi. Before I do anything, I need to debug and see where am I at the code in order to print some messages. For that, I will be using the serial.begin method in order to enable some, let's say, debugging. I will give the baud rate as 115200. This will be used only for printing messages on the console. And then for the server, we need some couple of things to be defined. In order to make the server accessible by us, we need to set a specific IP address, because if you let the router to specify this IP address, you know these are dynamic. Every time the server IP address will be changed. So in order to make this IP address or let's say force it to be the one we need, then we need to define it, and we can use the IP address data type and just say, call it an IP. I'll use 192.168.maybe 2.0. You can use any name. Oh, sorry, it's not a dot, it's a comma. And yeah, you know, it has to be dotted. You can use a character array even to use the dotted format. Remember, this could be random. Okay. And then we go to something else called the gateway. And I will define this later. And then we go again back to the subnet mask. This subnet mask also could be random, but we need to know that the IP address uses values from 0 to 255. You can use whatever you want in the IP and the subnet mask. So for this, I will be using 255, 255, 255, maybe 0 at the end. And then now I'm good to go. So in order to force this IP address for our server, we can use the Wi-Fi.config method and just pass the information in this specific order: IP, gateway, and the subnet. Remember, this order is important. This actually will force the server IP. Okay, and then we just simply pass the parameters of the ID of our Wi-Fi network and the password to the begin method, Wi-Fi begin, in order to connect to Wi-Fi. So right now, it should be okay and should be connected after this line of code, but in order not to move on to the following commands, we need to make sure that we are correctly connected to the Wi-Fi before we do anything else. In order to do this, we will have a simple while loop and use the method called status, Wi-Fi.status. If it is not equal to well connected, that means we are not connected to the internet yet, then I'll put some delay, maybe half a second or 500 milliseconds, and then just print some dots or periods, so I know that we are still trying to connect. If this was successful, then we go and print that We are connected to the Wi-Fi. Connected to Wi-Fi. And then we can move on. Okay, so why I have stopped this gateway? Actually, this gateway has to be the same as your Wi-Fi DNS. Okay, how can I find this Wi-Fi DNS? First of all, I'm connected to my phone internet. I'll connect them to the Wi-Fi and show you. There could be some lag. Excuse me for this. Okay, now I'm connected to the to my my Wi-Fi access point. Let me share this with you. Okay, right now I'm in the settings, Windows settings. If you go to the network and internet and go to Wi-Fi, you'll see your Wi-Fi connected to, and then there's something called hardware properties. If you go into this hardware properties, you'll find something called IP 4th version DNS server. This IP doesn't have to be used because we say the IP for our server can be used, can be random, but this gateway DNS has to be used. So it is 192.168.1.1. We need to remember this. Let's go back to the code again. Okay, so in here we go again, 192.168.1.1, as we remember. Oops. 168.1.1. You can also use this format, the following format for this, like char IP equals 192.168.2.0. This is also acceptable by the Wi-Fi.config method. Okay, so what now we are now connected to the Wi-Fi, and we need to let the server do something about the web page and all of that. We have a method called, we first need to define the server, and this server is going to use the ESP8266 web server class, and we just call it a server and then give it the port. This port actually is going to be the TCP port you need to use, and as maybe computer engineers know, that the TCP port for HTTP code is going to be 80, and that's why we are using the port as 80. So 80 for HTTP port. All right. Okay. So now, before we begin the server, we need to define some methods, or let's say functions, to handle some actions accessed by the user. And in order to do this, we can use the server.on method, and we can give it the route. This route could be anything. Actually, we can start from the root path, which is defined in this way, and then just we give a handler function. Let's say it's a handle index, and we will define this handle index function. Basically, I want this handle index, whenever someone goes to the server, access the server, I want this handle index to run the to show a hello world message to the web page. So let me define it in here and say handle index. It is void and it is not accepting any parameter. And then we can use the method called server.send, and this send method asks for 3 different parameters. The first one is a code, which is an HTTP code. This code, actually, you might not know the 200, but if I tell you the most famous one, it's going to be much clearer for you. Whenever you go into a web page and the web page is not found, you will find a code called 404. That 404 is a HTTP code that shows this page is not found. However, the 200 code for HTTP is going to mean that we have a successful response. So we want this to be in our case. And then the second parameter will be the content type, and we can use the text plane. These are actually HTTP standards. Computer engineers know better than me. But you can use this text plane to make sure that the type is a text, and then just print the hello world message. Okay, so now everything is almost ready. We need only to go to the loop, and in order to call all of these things, we just basically use the handle server.handle client method in order to do all of this. Okay, for now, I'll just upload the code. The code is not ready, is not yet ready, but I will upload the code and see what things I can come up with. Okay. So if you are not having the ESP8266 boards installed, I'll share a link at the end of how to do it. But I'm using the NodeMCU version 1.0, this one, and I'm going to set the upload speed to maximum, not to wait too long, and then just specify the board, which is COM9. Okay. So let's verify the code, and while it is doing this, I'll need to change to my Wi-Fi connectivity. Okay, we need to remember this code 192.168.2.0. We'll be using this in our Google Chrome browser. Okay, we have no errors now. We can simply upload it, upload this sketch, and just wait for a few moments and see in the serial monitor if we are connected to Wi-Fi or not. Okay, uploading is done. Now we are waiting, still inside the loop. Hopefully it connects. I think you're not seeing this. Let me share it with you. Yeah, this is the COM port. We are trying to connect. This is the serial monitor. You see now we are inside the loop we specified. Still not able to connect. Oops, it's my fault. I'm sorry, guys. All right, I made a mistake in the Wi-Fi access point name. It has to be quarantine as shown in here. Yeah, quarantine, and this is Q2020 at 2020. Okay, now everything should be fine. Let me upload this sketch again and see what this serial monitor is going to show us. It's not yet uploaded. Now uploading. Okay, we are trying to connect to the Wi-Fi. Yeah, if you go to the end, we are connected to Wi-Fi. So if we go now to the browser, I'll use the Google Chrome. And as I told you, we need to remember the server IP address. It was 192.168.2.0. If I enter, I should be able to see the hello world message. And let's see what happens. This is the root path and defined by the / in the code. Sorry, the internet connectivity is not so high, so we need to wait. Took too long to respond. Maybe there is a problem in the connectivity. It seems there's something wrong with the connections. Let me try one more. All right, all right. Sorry for this stupid mistake. I forgot to start the server, and I need to use the server.begin method. It's my fault. Sorry. Okay, now we are connected to Wi-Fi. We are good to go to this back and just update the page, refresh it.
Bekawi, do you have a firewall?
I'm not sure. I don't think so.
Because if your firewall is not allowing it, you may need to disable it.
Actually, I have tried this before, but there could be something wrong. Let me check the code again and
Sure.
see 168.20. I'm using this Wi-Fi config. Everything seems fine. But no idea why it is. All right, let me try to reset.
Also, check if you've saved it. Hit Control S to save it once.
To save the code, you mean?
Maybe it doesn't automatically save.
Okay, I'll try to upload it again because everything should work fine. Let me try to use another board as well. Okay. It seems there's a traffic on the Wi-Fi connection. Maybe that's why it's not being able to show it. Okay. Okay, we are connected to Wi-Fi. Again, there could be. Okay, let us do something and check if the server is going into the handle index method. Just do a print line. I'm in. Okay. Still nothing. Just bear with me. I'll try to fix this. Okay, let's go back to the server and try to change this one maybe to 1 and check what will happen. This should work. Okay, now it is working. No idea why D2 was not working. Sorry for taking your time, guys, for this. And let's go back to our server code. Okay, so now we have seen the hello world message printed whenever we access this IP address. Okay, now we want our server to do other things like getting the information from the other clients and update them to the same web page. So before going into updating the values, we need to have a string. Maybe I'll call it show. As I said, we will be having different values from different clients. We'll have the button state and the potentiometer value. So I need to define these variables. I'll have them as an integer, and maybe I call this an ADC value. Okay. So in here I'll say that the button state equals plus. This plus actually is a concatenation between two strings in the string object, if you are not familiar with the C++ coding. And then we take the string format of our button state, and then we just add a termination character at the end. And we take this show and add to it the ADC value equals, again, the string format of the ADC value variable. And no need to.
Abdel, can you project the code, please?
Oh, you're not seeing. Sorry for that. I'm sorry. I was talking about this handle index method. Instead of having the hello world message, I'll have a string called show to include both information being read by the from the clients as a button state and ADC value. We have this show message as a button state is equal to, then plus. This plus is the concatenation between two different strings in C++ objects. And then we convert this button state to a string format, and then we just add a termination character, or we can ignore this if we want them to be on the same line. Same for the ADC value, and then we add this ADC value. Instead of having this hello world message, we just pass the show string we just created, and then we are good to go. Again, if I upload this again to the server, I need to see, instead of the hello world message, the button state equal, and then some garbage value, ADC value is equal, then some garbage value, because we haven't got them from the clients. Okay, let's upload it and see what will happen. Done uploading. Trying to connect to Wi-Fi. Okay, now we are connected. Now we go to the Google Chrome again and just refresh this page. As you can see, this the web page, right? Yeah, okay. I'm already sharing. So you see in here we have the button state is equal to 0, the ADC value is equal to 0. These are the values going to be read from the clients. Okay, now we have set everything up almost for the server. Instead, except for updating the values, we need to receive them from the clients, and we need to add one more page. So let's get back to the code and continue. Okay, so now we have this method is going to be displaying the root path will be displaying only the values. Now we can have another one called maybe I'll say it is update, and then just pass a function. I'll call it handle update. Okay. I'll also add another one, and this one is going to be using the web page to toggle the LED connected to the server, and just simply call it toggle and give this a function of toggle. Okay, so let me define these functions. Void handle update. All right. Inside this handle update, we can use the method called server.arg in order to look for some arguments and get the values of them. They will be in string format, so we can use this server.arg, and we will be looking for maybe an ADC value written in this way by the client. We'll make sure to have this ADC value is the same as in the client code, and then this one will give us the string format, but we need it to be an integer. Then we use the toInt method to convert it to integer. We do the same thing for the button state and say it is equal to server.arg, and maybe a button state going to be used. We need again to convert this to an integer. Okay. By this, we'll be this ADC value and the button state will be updated whenever we go into this update, and this will be used in the client. I will show you in a bit how to do this, and then the values will be displayed. Okay, now we need also the other function to handle the toggle. All right, for this handle toggle, sorry, I'll use a character array to define my web page. It's an HTML web page. If you are not familiar with HTML, don't worry. I will explain the code. It will be super easy to understand. But before doing that, as we know, HTML code is much better if you write it row by row. In order to use this format, we have this ability in Arduino. Use the capital R, then 5 equal signs. But before that, we need the quotation, and then an opening parenthesis, go to the end, closing parenthesis again 5 times, and then you close it this way. Now we can use each row of this R to write our HTML web page. Okay, but before going into that, this web page is going to be used using or occupying the RAM of our ESP8266, and the RAM is too limited to 50 kilobytes. In order to, and we have a built-in flash in this ESP8266, then why not to use this flash? In order to use this flash, save this web page on it, we use only a simple word, which is called prog_mem. And then we are good to go with the HTML coding. We have something called the HTML tags, and these are basically the opening and closing parentheses or curly brackets, the same as these. I mean, you'll open it. This one is actually this way. It is the opening curly bracket, and then you go for the closing curly bracket, and it is going to be this way. Okay, inside the HTML web page, we go and just add the body. Again, we use these tags again. If you are familiar with HTML, you will do better than me. But in this case, I will just add a simple push button to the toggle in order to toggle the LED state of the server. Inside this body, we'll be using something called forms, and the action of these forms is going to be doing nothing in terms of the web page. And we close our form. Inside our form, we'll have the button, the push button, and in this push button will have a name displayed on it. Then I will call it only LED toggle, and then the closing of this button. Now I have created a very simple HTML code that HTML web page that will have a push button inside it called an LED toggle. Okay, we need to define as well the pin number. I'll call it an LED, and then this pin number is connected to D0. And then just in the setup, I specify in here that LED pin is going to be output. And simply in the toggle bin, whenever this toggle is accessed by the web browser, I need to digital write in order to bypass the information to the LED, and write to the LED, and then again to convert it, I'll use the digital read to read the current status and just convert it of the LED, and then close it. So right now I have done everything except to show this push button on the web page. To do this, we have seen it, server.send again 200 for a successful response. But the different thing in here, we'll be using the text HTML type, because this web page is an HTML web page, and then just we pass the web page variable. By now, we are good to go. The server is basically done. So let's upload this to our server and see what happens. Let me connect my phone to show you. Okay, yeah. This needs to be declared on the top because we are using the program as a global variable. Okay, now we are uploading. Done uploading. Let us see if we connect to Wi-Fi. Now we are connected to Wi-Fi. Let me share with you the Google Chrome. Now, if I go to toggle, I should be able to see the push button in there. Okay, now we can see this. Oh, sorry, the comments, because this is an HTML web page. These comments will be shown. Let me upload this again. Okay. And let me just refresh this. Yeah, now we can see the LED toggle. Let me share my phone screen. Okay, now I'm in the browser. As you can see, here's my phone screen. When this is the server I'm connected to, and you can see the LED now is on. If I press on the button, it should go off. Oops. Okay, let me just pin this to one of the sides, or maybe just have this in here. Oops. Okay. So now, when I press on it and wait for it to refresh, the LED should go on, you see? And again, it will go off, depending on the speed of the internet. Okay, now we have set our browser, our server, sorry. So let's go and create a new one for the client. This is the sketch. Okay. I'll try to do this faster. Client. Okay. And the client, we only have to include the library to connect to Wi-Fi, which is the ESP8266 Wi-Fi H. Again, Wi-Fi credentials. Okay. And then we will use the Wi-Fi client class to define our client. We don't need to set the IP address. We don't care about the IP address of the client. So let the Wi-Fi dynamically assign the IP address to it. Again, we go back here and just use the begin method of the Wi-Fi, pass the ID and the pass. Again, for debugging, we'll be using the serial that begin with this baud rate. Then again, the same check, Wi-Fi.status is not equal to well connected. A symbol delay of half a second, and just print some periods. Okay, and then we say serial.println connected to Wi-Fi. Okay, so right now the client is ready to be set, but before doing this we need to define also the port to read. Maybe this one will be the button client, button state, and it is connected to pin D3, and we define this pin as the input, but as I said, it's going to be an input of type pull up. Okay, this pull up will if you are not touching the button, it will be always high, like 5 volts or true, and whenever you press the button it will go to ground or 0, low. This is the pull up term, is what is going to do. So now in order to connect to the server, we use a method called client.connect, and we'll use the host IP and the port, which is 80. This host, we again go and define it as a character array, and this host is going to be exactly the same as the server we had. This is the same in the server. This is the server IP, and this is going to be our host in here. And if this is true, let's do something else. That means we are having some connection errors. Just we stop the connection, and in order for us to know that there's a connection failure, and then at the end, either way, we need to stop and say we are disconnected. Okay, so now if we are able to connect to the server, then we can do everything we need. First off, let's begin with the button state. To read the button state, we use simply the digital read function in Arduino, and we read the button. And maybe let's show this as well. To check, maybe let me add. Okay, and then we need to have the HTTP request, and it will take the following form. We remember that we will be using the /update in order to update these values. The way to do this HTTP request is going to look like this. We use a URL variable and set it to /update and then a question mark. Whatever after this question mark is going to be passed as the argument, and then we use the button state and make sure this button state is exactly the same in the server, is defined in the same way in the server, and then say equals, and then just concatenate the string format of the button state. Then we initiate another variable, which is the request itself. For this, we'll be using a method called, this is going to be an HTTP method, and it is going to be get method. This is one of the important things to be done in the request. And remember this minimum requirements for an HTTP request. I'll use the minimum. After we define this get, we add the URL to it, and then we add the HTTP version we are using. It is 1.1, and then /r/n, and then we add the host information or the server, and this is going to be the host. And remember, if you want to use the host in here, you have to use the character array, otherwise you cannot pass it into this string. If you use IP address instead of the character array, you won't be able, you'll get an error. So you have to use it in this way. And then /r/n. And then you add the connection type. In my case, I'll make it to keep alive. All of these are HTTP related. If you are familiar with HTTP, you know why we are using this. If you are not, you can use these without even knowing them. And then we are done with this request. Okay, so we have the request. We need to send it. How are we going to send it? We just use the client.print. Remember, this client.print is not the same as the serial.print. Client.print is going to send this information to the server that is connected to it in here. So client.print, and just pass this request as the parameter. So now we are good to go. We almost finished. But if the server is going to send us any information, then at the end here we can use something called the client.read string until, and then maybe we use any of the characters used by the server, maybe the termination character or any character you want to look for. But we are not going to receive anything from the server. We are going to be only updating the values. And so by the end of this, we are good to go to upload this code to the first client. The first client is connected to a NodeMCU with the button connected to it. So let's hit the upload and see what are the outputs. Just give it a second. Now uploading. And let's see the serial monitor. Connected to Wi-Fi. As you can see, the button is equal to 1, and then we disconnect. After we do every request, we disconnect in this. Let me show you in the code. And here, after we finish this request, we go stop and disconnect. So now we should, when we go to our web page, we should be able to see this information. Now the button state is going to be 1. Oops. Oh. Why is it so? Let me check the server. I didn't change anything. Why is it the hello world message? Let me upload the code for the server again. Okay, so let's check the client. Now the button state is 1. When we refresh, we should see 1. You see? Am I sharing this one? Yeah, okay. So if I trigger the button and refresh again, it should go to 0. Let me check the client. Is it changing to 0? No. Just wait a bit. It's not changing in the... All right, I'll connect this to ground. Simply. It seems the button state is not being updated. Okay, I'll check this at the end. The button state is not being updated. So let me share with you the client code. So now we have finished the first client code. Now we can go to the second client. We can use this one actually to modify. We can modify this one and give it to the second client. We need only to change this one to maybe a potentiometer, we call it, and then it is connected to the A0 port. We change it as well in here, a bot, and it is only an input. And we go to, instead of digital read, we have the analog read, and in here we have the ADC value. Okay, wait, yeah, the ADC value. ADC equals, and simply we pass this ADC value, and then we go ADC value. We have to make sure this one is written in the same way written in the server, and then we add ADC value, and that's it. These are all the needed changes. Then we can connect our third client, all right, which is the Wemos D1 Mini, connected to a potentiometer through the pin A0. And I need to change the port type, going to this one, upload speed set to max, choose the correct port, then upload. Just wait for it to... Oh, sorry. This has to be the bot. Okay, let me share with you the share monitor. You see now the values we are receiving. I can change them according to the potentiometer. So let's set it at 700 something in here and check what is the server receiving. It could take a couple of seconds, couple of refreshes. You see, now we are receiving, oh, sorry. I need to share this one. Yeah, you can see now when I refresh it, it takes a couple of seconds. Now we have this 725 ADC value updated in the web page. So now we have seen everything in action, all the clients and server connected together. So before we move on to the Q&A session, I need to emphasize that this implementation has a limitation, as you need to be connected to the same Wi-Fi access point in order to in order to be able to use them. All of them, the clients, the server, and even the web browser you want to use has to be connected to the same point, access point, the Wi-Fi point. That means it will limit you maybe inside your house or your facility. So I'll ask Amina to start the Q&A session. And sorry for taking your time. Thank you for being patient.
Thank you. And if anybody has any questions, please use the chat option or even unmute yourself and ask directly, please.
Even if we have questions to Professor Erhan Ince, he is with us in the line. You might ask him as well regarding his presentation.
Yes, I'm here if you have questions.
You can also ask about future sessions, what will happen, what will be the end result, what you're going to get from this course, on and on.
Hello.
Yes.
Hello.
Thank you for organizing this, and I have quick question. So actually, I'm not electrical engineering student, but I want to know that how we can use this the Wi-Fi controller and this stuff for 4.0 as a loop. You make it just once and you just randomly started, and I want to know how we can use it like loop. It's working by itself. Thank you.
You're welcome. Okay. So if you meant that how is it going through the loop, I'll share the screen of the server code. At the end, inside the loop, we have this handle client. It is going through the every one on pages, every path you trigger, and then it will go to the handle update, handle toggle, and handle index. But if you're talking about making this automated, like refreshing itself without the need of us to refresh it, then I think there is a parameter in the, let me share the client, and HTTP guys know better than me. Inside this request, there is something called, let me add as a comment, a refresh, and then you specify the seconds to refresh itself automatically this way. And maybe you'll need to add the /r/n as well. By this way, sorry, I need to connect to my Wi-Fi network, to my phone, sorry. Just bear with me. Okay, So you see, you can use this parameter refresh every 5 seconds and include it in the request in here. This is to be refreshing every 5 seconds. Is this answering your question?
Yes, yes. That's what I mean. Thank you so much.
You're welcome. Okay. Any other questions? Yes,
Osama, can you raise your hand?
Yes, hello?
Yes.
Yes, first of all, I want to thank you all, especially Professor Erhan and Engineer Abdel for this valuable information.
thank you.
And I have a question for Professor Erhan.
Yes, I'm listening, Osama.
Yes, I want to ask the sir about the wireless communication. Serial or parallel? If none of them, what type is it?
Of course, you have heard of TDMA, right? Time division multiple access.
Yes.
Right. In time division multiple access, you're trying to share the time and get the number of bits from each source, each channel. So yes, it has to be serial and in a high capacity. I mean, because you want to use a high capacity link like under the ocean cables they put between continents, for example. You want to send lots of information. So you want to use many channels, and by time sharing between the sources, you want to get information and multiplex it into one serial stream. So in a sense, if you're using TDMA, it will be serial.
Okay, thank you very much, sir.
You're most welcome. Of course, it's application based, Osama. And, you know, you also maybe you have heard of OFDM.
Yes, I heard it once, I think.
Yeah, in OFDM, for example, you have parts of the system where you need to go from serial to parallel. So it's based on what sort of application you have and what is being used. If you're using something like WiMAX with OFDM, it's maybe different. If you're using TDMA, it is different. Okay.
Okay, thank you very much, sir. Thank
You're
you.
welcome. Bekawi?
Yes, sir.
Perhaps you can say to our audience, you have some hardware, some firmware that you're using. Maybe how you acquired it and how much it may cost. So if anyone interested in repeating what you did, they have a means.
Yeah, actually, I'll be sending out to those who are registered, who has registered by their emails. And if anyone who is not registered, please leave your email in the chat session. I'll send it. I'll be sending all the links and the coding, everything. If you want to use these ESP8266, I'm not sure where to find them in Cyprus, to be honest, but you can order them online. But this could take a while for you because we are in this pandemic. But it is not costing too much. Maybe each ESP is going to be $3 to $5 maximum, with the added shipping cost depending on the shipping method.
I just wanted to add that if anybody wants to recreate this by themselves, this session is being recorded and the recording will be shared also.
Yeah. Thank you, Amina.
Yes, thank you, Amina.
Does anybody else have any questions? All right. I took a list of the participants. Hopefully, we'll see you again next time. This about wraps it up for today's course. Great thank you to Rahman and to Professor Ince and to everyone who dedicated their time to attend. I hope you all have a great night. And yeah.
Thank you, Amina, and thank you for giving us this opportunity to get together. You know, COVID-19 has put everyone in an awkward position, most of the time doing things online or just staying at home.
Yeah.
So it's something different to do, and maybe for those who have tendency to write codes, this was interesting.
Yes, it's more on the practical side also.
Of course.
Thank you so much, everyone, for attending, and thank you, Professor Erhan. Thank you, Amina, and the Syrian Society President. Thanks all for making this happen, and I hope you enjoyed it.
Thank you, all of you. Thank you.
Thank you, Abdel.
And hope to see you again on 19th, inshallah.
Yes. All right, everybody, take care of yourself and stay
Bye.
safe.
Yeah, you
Good
too.
evening. Good evening.
Good evening.